Let us begin very gently. Temperature is something we all experience every day. We feel warmth from the sun. We feel cold on a winter night. But in physics, temperature is not a feeling. Temperature is a measure of motion. More precisely, it measures the average kinetic energy of particles, atoms and molecules inside matter. When something is hot, its atoms vibrate rapidly, molecules move aggressively, energy flows outward. When something is cold, motion slows, vibrations weaken, energy becomes scarce. Temperature is not about how much heat something has, but about how fast its particles are moving. This distinction is important, and we will return to it many times. Classical view of temperature. In classical physics, higher temperature equals faster motion, lower temperature equals slower motion. So naturally, physicists once asked a simple question. What happens if motion slows down completely? If all particles stop moving, what temperature would that be? This question leads us directly to the idea of absolute zero. Absolute zero is defined as 0 Kelvin, or minus 273.15 degrees Celsius. It is the lowest possible temperature according to thermodynamics. At this temperature, no thermal energy remains, no heat can be removed. Classical motion reaches its minimum. The Kelvin scale was introduced because Celsius and Fahrenheit are arbitrary. Kelvin starts at a true physical zero. 0 Kelvin means zero thermal motion in theory, but theory and reality are not always the same. The third law of thermodynamics. The third law of thermodynamics states it is impossible to reach absolute zero in a finite number of steps. No matter how advanced your technology, you can approach absolute zero, but you can never reach it exactly. Each attempt to remove the last bit of energy requires more effort than the previous, produces diminishing returns, eventually becomes impossible. This is not a technological problem, it is a law of nature. Reference: Walther Nernst, The Third Law of Thermodynamics, 1906. Absolute zero is not just cold, it represents a boundary, a limit, a mathematical edge of reality. At this boundary, classical physics begins to fail. Quantum physics becomes unavoidable, and this is where things begin to change. Now we step carefully beyond classical thinking. In classical physics, perfect stillness is allowed, zero motion is possible, but nature does not operate purely on classical rules. At very small scales, the universe follows quantum mechanics, and quantum mechanics introduces a deeply unsettling idea, the Heisenberg uncertainty principle. One of the foundational laws of quantum physics states you cannot know both the exact position and exact momentum of a particle at the same time. This is not due to bad instruments, it's not due to human error, it is a fundamental rule of reality. Reference: Werner Heisenberg, Über den anschaulichen Inhalt der quantentheoretischen Kinematik und Mechanik, 1927. Momentum is directly related to motion. If a particle were completely motionless, its momentum would be exactly zero. Its position would need to be perfectly known. Quantum mechanics forbids this. So even at absolute zero, particles must retain some motion. Energy cannot fully vanish. This unavoidable residual energy is called zero-point energy. Zero-point energy explained simply. Zero-point energy is the lowest possible energy a system can have, energy that cannot be removed, motion that cannot be stopped. Atoms continue to vibrate slightly, fluctuate subtly, resist complete stillness. Perfect rest would violate quantum law, so the universe refuses it. A quiet but profound truth. Even at the coldest imaginable temperature, atoms still move, energy still exists, silence is never complete. Absolute zero is not empty, it is quiet motion, not no motion. Imagine the coldest place possible. No warmth, no sound, no visible motion. Yet beneath this stillness, particles gently vibrate. Energy quietly persists. Reality refuses to turn off. This is not poetry. This is physics. As temperature drops closer and closer to absolute zero, matter begins to behave in unfamiliar ways. At ordinary temperatures, atoms behave like individuals. Collisions are frequent, random motion dominates. But as thermal energy fades, disorder weakens. Collective behavior emerges. Quantum effects grow visible. Cold does not merely slow matter down, it reshapes how matter exists. Quantum statistics take over. At very low temperatures, particles no longer follow classical rules. Instead, they obey quantum statistics. Bosons follow Bose-Einstein statistics. Fermions follow Fermi-Dirac statistics. This distinction determines how matter behaves near absolute zero. Reference: S. Bose in 1924, A. Einstein in 1925, Foundations of Quantum Statistics. Let us slow down here. This is one of the most important discoveries related to absolute zero. What is a Bose-Einstein condensate? When bosonic atoms are cooled to near absolute zero, their wavelengths expand, individual identities blur, particles overlap. Eventually, millions of atoms collapse into a single quantum state. The state is called a Bose-Einstein condensate, or BEC. In a BEC, all atoms behave as one entity. The system is described by a single wave function. Matter becomes visible quantum mechanics. Experimental confirmation. Bose-Einstein condensates were predicted in the 1920s, but not observed until 1995. Reference: Eric Cornell and Carl Wyman. As temperature drops closer and closer to absolute zero, matter begins to behave in unfamiliar ways. At ordinary temperatures, atoms behave like individuals. Collisions are frequent, random motion dominates. But as thermal energy fades, disorder weakens. Collective behavior emerges. Quantum effects grow visible. Cold does not merely slow matter down, it reshapes how matter exists. Quantum statistics take over. At very low temperatures, particles no longer follow classical rules. Instead, they obey quantum statistics. Bosons follow Bose-Einstein statistics. Fermions follow Fermi-Dirac statistics. This distinction determines how matter behaves near absolute zero. Reference: S. Bose in 1924, A. Einstein in 1925, Foundations of Quantum Statistics. Let us slow down here. This is one of the most important discoveries related to absolute zero. What is a Bose-Einstein condensate? When bosonic atoms are cooled to near absolute zero, their wavelengths expand, individual identities blur, particles overlap. Eventually, millions of atoms collapse into a single quantum state. The state is called a Bose-Einstein condensate, or BEC. In a BEC, all atoms behave as one entity. The system is described by a single wave function. Matter becomes visible quantum mechanics. Experimental confirmation. Bose-Einstein condensates were predicted in the 1920s, but not observed until 1995. Reference: Eric Cornell and Carl Wyman, Nobel Prize in Physics 2001. This discovery proved quantum theory governs reality even at macroscopic scales. Absolute zero reveals laws hidden at higher temperatures. A sleep reflection. Imagine matter losing its individuality. Not chaos, not collapse, but unity. Near absolute zero, separation itself fades. Fermions and the Pauli exclusion principle. Not all particles merge peacefully. Fermions, such as electrons, follow a different rule, the Pauli exclusion principle. This principle states no two fermions can occupy the same quantum state. Reference: Wolfgang Pauli, 1925. At near absolute zero, fermions stack into layers of energy. Motion does not vanish. Pressure remains without heat. This creates something remarkable: degeneracy pressure. Even at zero temperature, fermions resist compression. A pressure remains with no thermal origin. This pressure supports white dwarf stars, prevents matter from collapsing. Absolute zero does not mean weakness. It can mean resistance. Entropy is often misunderstood. Entropy is not chaos. It is the number of possible microscopic arrangements. Entropy near absolute zero. As temperature decreases, accessible microstates decrease. Disorder diminishes. Entropy approaches a minimum. According to the third law, a perfect crystal at absolute zero has zero entropy. But perfect crystals do not exist, so in reality, residual entropy often remains. Disorder is reduced, not eliminated. Reference: R. Fowler and G. Guggenheim, Statistical Thermodynamics. Time and entropy. Time is deeply connected to entropy. The arrow of time follows entropy increase. At absolute zero, no thermal change, no entropy increase, no classical processes. Some physicists suggest without entropy change, time loses operational meaning. Time may still exist, but it has nothing to act upon. The absolute zero vacuum at absolute zero. Now we move beyond matter. Even if all particles are removed, all radiation is eliminated, all temperature reaches zero, something remains. Vacuum is not empty. Quantum field theory tells us every point in space contains fields. Fields cannot be fully turned off. Energy fluctuations remain. This lowest energy state of space is called the quantum vacuum. Virtual particles. In the quantum vacuum, particle-antiparticle pairs appear briefly. They borrow energy within allowed limits. They vanish before detection. This is not metaphor, it is experimentally verified. Reference: Casimir effect, Hendrik Casimir, 1948. Absolute zero does not silence space. Even at absolute zero, fields fluctuate, energy exists, space vibrates. Nothingness is forbidden. Human technology has come astonishingly close to absolute zero. Using laser cooling, magnetic trapping, evaporative cooling, scientists have reached temperatures billionths of a Kelvin above zero. Reference: MIT and NIST ultra-cold atom experiments. Yet, absolute zero itself remains unreachable. Each step closer becomes exponentially harder. The boundary holds. In modern physics, absolute zero is no longer just about cold. It is about control. Quantum computers and cold. Quantum systems require isolation, minimal thermal noise, extreme cooling. Many quantum processors operate millikelvins above absolute zero. Cold becomes a tool to preserve quantum coherence, reduce decoherence, access fragile quantum states. Absolute zero is now a technological frontier. The early universe was hot. The far future may be cold. As the universe expands, energy spreads thinner, stars burn out, motion fades. Some cosmological models suggest that the universe approaches a cold, quiet state, not absolute zero, but asymptotically close. This is called heat death. Reference: Lord Kelvin, Modern Cosmological Thermodynamics. In quantum mechanics, every physical system has what is called a ground state. The ground state is the lowest possible energy configuration, not zero energy, not complete stillness. At absolute zero, systems occupy their ground states. Energy cannot be extracted further. Motion persists in constrained form. This means absolute zero reveals the irreducible structure of matter. Reference: Sakurai, Modern Quantum Mechanics. Ground state is not empty. Even in its ground state, an atom has electron probability clouds. A molecule has vibrational modes. A crystal has lattice zero-point motion. The idea of frozen matter is false. Matter remains active, but activity becomes subtle and structured. Let us consider a crystal. Atoms are arranged in a lattice. At high temperature, they vibrate strongly. Thermal noise dominates. At near absolute zero, thermal vibration disappears. Zero-point vibration remains. This motion cannot be removed, prevents perfect rigidity, determines material properties. Consequences of zero-point motion. Zero-point motion affects electrical conductivity, alters mechanical stiffness, limits precision measurements. Even the hardest solids are never still. Reference: Ashcroft and Merman, Solid-State Physics. Near absolute zero, some fluids behave in impossible ways. Superfluid helium. When helium-4 is cooled below 2.17 K, viscosity disappears, flow becomes frictionless, fluid climbs walls, rotation becomes quantized. This state is called superfluidity. Reference: Kapitsa in 1938, Allen and Missener in 1938. Meaning of superfluid motion. In superfluids, motion exists with no energy loss. Flow is governed by quantum phase. Circulation occurs in discrete units. Cold does not remove motion. It purifies motion. A similar phenomenon occurs with electricity. Superconductors. At low temperatures, electrical resistance drops to zero. Current flows indefinitely. Magnetic fields are expelled. This happens because electrons form Cooper pairs. Pairs behave as bosons. Quantum coherence emerges. Reference: Bardeen, Cooper, Schrieffer, BCS theory. Absolute zero and infinite current. In principle, a superconducting current can persist forever, without energy input, without decay. This challenges classical intuition. Cold does not kill activity, it locks it into coherence. At ordinary temperatures, phase transitions are driven by heat. Near absolute zero, phase transitions occur due to quantum fluctuations. These are called quantum phase transitions. Quantum fluctuations dominate. At zero temperature, thermal noise vanishes. Quantum uncertainty remains. Phase changes occur through tunneling. This reveals quantum mechanics alone can reorganize matter. Reference: Sachdev, Quantum Phase Transitions. Here we encounter a subtle and often misunderstood idea: negative temperature states. In certain systems, temperature can become negative. These systems are hotter than any positive temperature. Negative temperature does not mean colder. It means energy population is inverted. High energy states are more occupied. Reference: Purcell and Pound, 1951. Negative temperatures do not violate thermodynamics, are only possible in bounded systems, exist above infinite temperature. Absolute zero remains the lower bound. As temperature decreases, measurement becomes harder. Interaction adds energy. Observation disturbs systems. At near absolute zero, even observation introduces heat. Perfect isolation is impossible. This places a fundamental epistemic limit. Some properties cannot be known without changing them. Modern physics describes reality using quantum fields, not particles. At absolute zero, fields remain. Ground states persist. Vacuum structure dominates. Vacuum energy density. The quantum vacuum has non-zero energy density, measurable physical effects, cosmological consequences. This energy may relate to dark energy, influences space-time expansion. Reference: Weinberg, The Cosmological Constant Problem. Temperature is frame-dependent. In relativistic physics, motion affects thermal perception. Observers disagree on thermal states. This leads to effects like Unruh radiation, observer-dependent vacuum states. Reference: Unruh, 1976. At absolute zero, even nothing depends on who observes it. Entropy is information. At absolute zero, information becomes maximally constrained. States become highly ordered. Degrees of freedom shrink, but information never vanishes. Even the ground state contains correlations, stores quantum information, encodes structure. Physicists now use near-zero temperatures to simulate black holes, model early universe conditions, explore exotic space-time analogs. Cold laboratories now probe quantum gravity analogs, emergent space-time behavior. Reference: Ultra-cold atom analog gravity experiments, 2020s. At absolute zero, physics still asks, is space-time itself quantized? Does vacuum energy gravitate fully? Can absolute zero exist locally in curved spacetime? Is there a deeper limit beyond temperature? These questions remain unanswered. At absolute zero, every physical system is forced into its ground state. But a ground state is not a simple thing. It is not empty, featureless, silent. A ground state is structured, defined by symmetry, constraints, quantum correlations. In many body systems, ground states can be highly complex. Order can exist without motion. Structure replaces randomness. This tells us something fundamental. At the lowest energy, reality does not simplify, it reorganizes. As temperature decreases, thermal noise fades. Quantum correlations strengthen. Near absolute zero, entanglement dominates. Particles no longer behave independently. Their states become linked, non-local, inseparable. Ground state entanglement. Even in perfect isolation, ground states are entangled. Correlations persist across distance. Information is distributed, not localized. The background info is Amico et al., Entanglement in Many Body Systems, Review of Modern Physics, 2008. Absolute zero does not isolate particles, it binds them more deeply. At very low temperatures, quantum coherence lengths increase, wave functions extend, spatial separation loses clarity. In systems like superfluids, condensates, quantum Hall states, space becomes emergent, collective, context-dependent. Space as an emergent property. Some modern theories suggest space is not fundamental. It emerges from quantum correlations. Temperature hides this emergence. Near absolute zero, the scaffolding of space begins to show. The background info is Van Ramsdonk building up spacetime with quantum entanglement, 2010. Time, like temperature, has a direction. That direction is set by entropy increase, irreversibility. At absolute zero, entropy change halts. Classical irreversibility disappears. Does time still flow? Quantum mechanics allows reversible evolution, no preferred direction. At zero temperature, time symmetry becomes visible. Past and future become interchangeable in equations. This suggests the arrow of time may not exist fundamentally. It may emerge from heat. Measurement always involves interaction. Interaction always involves energy. At near absolute zero, even minimal measurement perturbs systems. Observers cannot be neutral. Knowledge becomes invasive. Observer as a heat source. At these limits, observation injects energy. Measurement creates temperature. Knowing disturbs being. This reinforces a core idea. At the deepest level, reality cannot be passively observed. The background info is Quantum Measurement Theory by von Neumann. Near absolute zero, new forms of matter appear. These are not defined by symmetry breaking or local order, but by topology, topological phases. In topological states, properties are global, robust against noise, immune to small disturbances. These states only stabilize at low temperatures. reveal structure beyond local physics. The background info is Hassan and Kane, Topological Insulators, 2010. Absolute zero exposes geometry hidden in matter. At zero temperature, systems can balance exactly between phases. Small changes cause large effects. Fluctuations span all scales. This point is called a quantum critical point. At quantum criticality, no characteristic length scale, no characteristic time scale, behavior becomes universal. This resembles early universe physics, black hole horizons, strongly correlated spacetime. Reference: Hertz, 1976, Sachdev, 1999. Why can we never reach absolute zero? Because cooling requires energy exchange, contact with environment, entropy disposal. As temperature decreases, heat extraction becomes less effective, entropy removal approaches zero, cooling stalls. This is not practical failure, it is logical necessity. Black holes possess temperature. This temperature is proportional to surface gravity, decreases as mass increases. Theoretically, an infinitely massive black hole would approach absolute zero. Reference: Hawking, 1975, Black Hole Thermodynamics, Zero Temperature Horizons. At zero temperature, horizons become extremal. Time dilation becomes infinite. Information storage becomes maximal. This links absolute zero to event horizons, quantum gravity, information paradoxes. The vacuum of space has a temperature. The cosmic microwave background sits at 2.7 Kelvin. As the universe expands, this temperature drops. Space cools. Motion thins out, but never fully disappears. The universe cools forever without reaching absolute zero. At zero temperature, no thermal processes occur. Chemical reactions cease. Diffusion halts. But quantum processes remain. Tunneling, fluctuation, correlation. Change becomes rare, subtle, non-classical. Some approaches to quantum gravity suggest temperature may be emergent. Space-time may have a ground state. Geometry itself may fluctuate. At this level, absolute zero may correspond to minimal space-time excitation, not emptiness, but structure. Reference: Loop quantum gravity, String theory thermodynamics, various. Absolute zero acts as a conceptual wall, a mathematical limit, a warning against classical intuition. It tells us reality has a minimum activity level, but not a minimum existence level. As temperature descends, heat fades, noise dissolves, classical explanations weaken, but beneath the calm, quantum laws persist, fields fluctuate, information survives. Absolute zero is not a destination, it is a direction. Temperature has an upper limit as well as a lower one. At the opposite extreme of absolute zero lies the Planck temperature. The Planck temperature is unimaginably high, around 10 to the 32 Kelvin, where space-time itself becomes unstable, where known physics dissolves. Absolute zero and Planck temperature form two boundaries, one of minimum energy, one of maximum excitation. Between them lies all physical reality. This suggests temperature is not just a property of matter, it is a coordinate of existence. Reference: Planck units, Max Planck, 1899. As temperature approaches absolute zero, degrees of freedom freeze out. Only the most fundamental modes remain. This is similar to how high energies reveal particle structure, low temperatures reveal collective order. Cold becomes a microscope. It does not magnify objects, it removes distractions. Cold as a filter of reality. At high temperature, everything moves, details blur, noise dominates. At low temperature, only essential motion survives. Structure becomes visible, laws simplify but deepen. This is why ground states matter. Low temperature physics reveals universality. In modern theoretical physics, some of the deepest ideas connect temperature to geometry. One such idea is the holographic principle, temperature and space-time encoding. According to holography, information in a volume is encoded on its boundary. Thermal states correspond to geometric features. Temperature relates to space-time curvature. At zero temperature, certain geometries become extremal. Horizons stabilize. Entropy reaches minimal configurations. Reference Maldacena, ADS/CFT Correspondence, 1997. Some approaches suggest gravity itself may emerge from thermodynamics. Space-time curvature arises from entropy gradients. If this is true, zero temperature may correspond to a state of minimal gravitational excitation. This implies cold may reveal the skeleton of spacetime. Reference Jacobson, 1995, Verlinde, 2011. The vacuum is not unique. Quantum field theory allows multiple vacuum states, different ground configurations, distinct energy landscapes. At zero temperature, transitions between vacua cease. The universe settles into a local minimum, but not necessarily the lowest possible one. This opens the possibility of metastable vacua, false vacuum states, long-lived but not eternal configurations. A false vacuum appears stable, persists indefinitely, is not the true ground state. At zero temperature, thermal activation vanishes, only quantum tunneling remains. This means vacuum decay becomes rare, but never impossible. Reference Coleman and DeLucia, 1980. Absolute zero does not guarantee permanence, it guarantees quiet persistence. At low temperatures, short-distance fluctuations freeze out, long-range behavior dominates. This is described by renormalization group flow. As temperature approaches zero, systems flow towards fixed points, universal behavior emerges, microscopic details become irrelevant. Reference Wilson, Renormalization Group, 1970s. Cold reveals what truly matters. At zero temperature, characteristic energy scales vanish. Systems become scale invariant. This means no preferred length, no preferred time, no intrinsic size. This behavior mirrors critical phenomena, conformal field theories, certain space-time geometries. Conformal symmetry preserves angles, ignores scale. At absolute zero, some systems acquire conformal symmetry. Physics becomes independent of size. This symmetry simplifies equations, deepens structure, connects distant areas of physics. Reference Polyakov, Conformal Field Theory. At zero temperature, thermal entropy vanishes, but quantum entropy remains. This entropy arises from entanglement, correlations, non-local structure. Information is not erased by cold, it becomes encoded differently. Computation requires energy, state changes, entropy production. At absolute zero, classical computation halts. Quantum computation changes character. Landauer's principle states erasing information costs energy. At zero temperature, erasure becomes impossible. Information becomes permanent. Reference Landauer, 1961. Classically, nothing means absence. Quantum mechanically, nothing means lowest energy configuration. At absolute zero, nothing still contains fields, fluctuations, structure. Nothing is a state, not an absence. Different observers may disagree on temperature. An accelerating observer detects heat in a vacuum, experiences Unruh radiation. An inertial observer sees empty space. At absolute zero, one observer's vacuum may be another's thermal bath. Reference Unruh effect, 1976. Cold is not absolute for all observers. As we approach absolute zero, ordinary words fail, concepts blur, intuition weakens. Temperature becomes abstract, relational, context-dependent. Physics continues, but language lags behind. As temperature drops further, heat disappears, motion simplifies, laws become exposed, but reality does not stop. It rearranges itself into its most fundamental patterns. Absolute zero is not silence, it is structure without noise. For decades, absolute zero was only an equation, but modern laboratories have come astonishingly close. Using laser cooling, physicists can slow atoms by firing photons opposite to atomic motion, reducing momentum step by step, removing kinetic energy with extreme precision. This technique, called Doppler cooling, has been refined into magneto-optical traps, optical lattices, sub-nanokelvin regimes. Research fact: atoms have been cooled to below 100 picokelvin. Max Planck Institute, 2009. This is not theory, this is measured reality. Light itself does not have temperature, but matter interacting with light does. At near absolute zero, light slows dramatically in certain media. Photons couple strongly to atomic states. Quantum coherence dominates. Stopped light experiments. In Bose-Einstein condensates, light pulses have been slowed to meters per second. Some experiments temporarily halted light entirely. Reference: Howe et al., Nature, 1999. Cold allows control over phenomena once thought untouchable. At everyday temperatures, quantum effects average out. Classical behavior dominates. Near absolute zero, quantum mechanics escapes confinement, becomes visible, becomes tangible. Schrödinger's cat without metaphor. In ultra-cold systems, superposition occurs in macroscopic objects. Quantum interference patterns emerge. Large systems occupy multiple states. This is not philosophy, this is laboratory physics. Reference: Leggett, Macroscopic Quantum Systems. Why doesn't matter collapse? At zero temperature, thermal pressure vanishes, classical stability disappears, yet matter remains. Because of quantum degeneracy pressure, zero-point motion, Pauli exclusion. This is why white dwarfs exist. Neutron stars resist collapse. Matter survives without heat. Cold reveals why existence is possible at all. Noise is usually associated with heat, but at absolute zero, thermal noise vanishes. Quantum noise remains. This noise is fundamental, cannot be filtered out, limits measurement precision. Standard quantum limit. In ultra-precise experiments, zero-point fluctuations dominate. Measurement uncertainty persists. Reference: Caves, 1981, Quantum Noise in Interferometers. Even silence has texture. Modern atomic clocks operate at microkelvin temperatures, near perfect isolation. Cold improves stability, accuracy, time resolution. Cold atoms and time precision. The most accurate clocks lose less than 1 second over billions of years, depend on ultra-cold atomic transitions. Reference: NIST optical lattice clocks. Absolute zero is linked to humanity's best measurement of time itself. Ultra-cold atoms are now used to simulate early universe conditions, black hole horizons, expanding space-time analogs. These systems obey equations similar to cosmology, allow tabletop universes, reveal inaccessible regimes. Reference: Cold atom analog gravity experiments, 2010s, 2020s. Cold becomes a portal. As temperature drops, complexity reduces, fundamental symmetries emerge. Different systems begin to behave similarly, follow identical equations, lose historical detail. This phenomenon is called universality. Reference: Statistical Mechanics, Universality Classes. Cold reveals laws beneath laws. At near absolute zero, systems become extremely sensitive. Tiny disturbances matter. Small energies reshape states. This sensitivity allows precise control, but also instability. Reality becomes delicate, balanced, exacting. Even at zero temperature, some systems display chaotic dynamics, driven not by heat but by interactions. Quantum chaos does not resemble classical chaos. It appears in energy-level statistics, connects to black hole physics. Reference: Sachdev-Yeh-Kitaev model. Cold does not eliminate unpredictability, it changes its origin. To reach low temperatures, systems must be isolated, external influence minimized, but perfect isolation is impossible.
At near absolute zero, cosmic radiation matters, gravitational effects matter, quantum vacuum matters, even the universe intrudes. Imagine a world without fire, without warmth, without thermal motion, yet structure persists, fields vibrate, information flows. Heat is not required for existence. It is required for noise. Physics at absolute zero shows existence does not require activity, motion does not require heat, change does not require chaos. The universe is capable of quiet persistence, structured stillness, ordered survival. Temperature fades, classical ideas loosen, quantum structure takes over. Absolute zero is not the bottom, it is the clearest point from which reality can be seen. At everyday temperatures, time feels obvious. Clocks tick, processes unfold, causes precede effects. But physics does not define time this way. In fundamental equations, time is symmetric. Past and future are interchangeable. Direction is absent. The arrow of time emerges from temperature, not from law. Entropy as the clockmaker. Entropy increases because systems exchange heat. At absolute zero, heat exchange vanishes. Entropy production halts. The arrow of time weakens. Some theoretical physicists suggest without temperature, time may exist only as a parameter, not as experience. Reference: Carlo Rovelli, The Order of Time, 2018. Cold does not stop time, it removes its direction. At near absolute zero, something unexpected appears. Not stillness, but periodic motion without energy loss.
Time crystals break time translation symmetry, oscillate indefinitely, exist in ground states. They were once thought impossible. Now they are real. Reference: Frank Wilczek, 2012, Experimental Realization, 2017. At zero temperature, motion can persist, repetition can be eternal, change can exist without heat. Absolute zero and the fabric of causality. Causality relies on temporal order, energy transfer, signal propagation. At zero temperature, thermal signaling disappears, only quantum correlations remain. Entanglement without communication. Entangled particles correlate instantly, exchange no energy, respect relativistic limits. At zero temperature, entanglement dominates, causality becomes subtle, connection replaces transmission. Reference: Bell's theorem, aspect experiments. Some modern theories suggest geometry is not fundamental. Distance emerges from entanglement. Space is a secondary concept. At low temperatures, entanglement increases, geometry sharpens, space-time becomes well-defined. Cold as a geometric lens. In holographic models, zero temperature corresponds to extremal geometry. Space-time becomes rigid, fluctuations reduce. Reference: ADS/CFT zero temperature limits. Cold clarifies the shape of reality. At high temperature, systems fragment, parts behave independently. At low temperature, reductionism fails. Whole systems matter, collective laws dominate. This reveals a truth. The deepest laws are not found by breaking things apart, but by letting them settle together. Near absolute zero, correlations extend infinitely. Boundaries blur, locality weakens. This is observed in superfluids, quantum magnets, and topological states. Reference: Long-Range Quantum Order, Anderson. Cold allows order without rigidity, unity without force. Heat death imagines a cold, inactive universe, no work possible, no complexity. But physics says otherwise. At zero temperature, quantum structure persists, quantum vacuum energy remains, information survives. Cold is not death, it is quiet survival.